let me ask you a question. It kind of sounds like the start of a riddle, right? What could a fizzy drink, a piece of life-saving scuba gear, and the super thin air at the top of the world possibly have in common? Well, the answer connects all of them, and by the end of this, you're going to see exactly how. The key to it all is understanding this one core concept in chemistry: solutions. You know, the funny thing is, we almost never encounter pure substances in our daily lives. That's actually pretty rare. Pretty much everything we touch and see is a mixture of two or more things. And what's really wild is that the properties of these mixtures, what they do and how they behave, depend completely on their specific recipe. And I mean, these solutions are absolutely everywhere. Think about it. That brass doorknob, that's a solid solution of copper and zinc. The tap water you drink, it's a solution with fluoride ions dissolved right in it to keep your teeth healthy. And get this, even the IV drips in hospitals are super carefully made saline solutions, engineered to perfectly match the saltiness of our own blood. These aren't just random mixes, they're precise and they're critical. So how do you make one of these things? Well, it all boils down to two key ingredients. Let's break down the basic recipe. First up, the official definition. A solution is a homogeneous mixture. Now that word, homogeneous, that's the magic word here. It just means the mixture is perfectly, totally uniform. The little particles are so evenly mixed that you can't see the individual bits, and they'll never settle to the bottom. See, every solution has two parts. You've got the solute, that's the stuff being dissolved, and it's always the smaller amount. Think of it as the guest. Then you've got the solvent. That's the stuff doing the dissolving. It's the larger quantity, so it's the host. And here's the important takeaway. The solvent usually decides what the final solution will be like. So if you dissolve solid sugar into liquid water, you get a liquid solution. Simple, right? Now, just saying a solution is strong or weak is, a little vague. To be really precise, we have to answer the question, how much solute is actually in there? And that's where the whole idea of concentration comes into play. One of the most direct ways to measure this is with something called mass percentage. And it's pretty much exactly what it sounds like. We're just asking, if you had 100 grams of the final solution, how many of those grams would be the solute? That's it. You just take the mass of the solute, divide it by the total mass of the whole solution, and then multiply by 100. So, for example, if you see a bottle in a lab that says 10% glucose solution by mass, it's telling you that for every 100 grams of that liquid, exactly 10 grams are glucose, and the other 90 grams are the solvent, which is probably water. See? Super straightforward. Okay, but for chemists, one of the absolute most useful units is molarity, and we show it with a big capital M. Instead of just weight, this focuses on the actual number of molecules. A mole is just a word chemists use for a specific, really big number of molecules. So molarity is just the number of moles of your solute dissolved in exactly 1 liter of the final solution. So if a chemist hands you a beaker that says 0.25 m NaOH, they're telling you that they've dissolved exactly 0.25 moles of sodium hydroxide, and then they added just enough water to bring the total volume up to precisely 1 liter. But what if you're dealing with crazy small amounts of something? We're talking like a single drop of something in an entire swimming pool. That's where parts per million, or ppm, comes in handy. It is the perfect tool for measuring stuff that's only there in tiny, tiny trace amounts, like pollutants in the air or minerals in your water. And believe me, these trace amounts can have huge effects. Let's take fluoride in water again. A tiny bit is awesome for preventing cavities. But get this, just 1.5 parts per million, an unbelievably small concentration, is enough to cause a condition called mottling on teeth. It's a really powerful reminder that in chemistry, how much is just as important as what. So can you just keep dissolving something forever? Like, can you just keep dumping sugar into your iced tea? Of course not. Every solvent has a limit, a point where it's just full. So let's talk about what happens when a solution hits that limit. This limit has a name. It's called solubility. It's the absolute maximum amount of a solute you can possibly dissolve in a certain amount of solvent at a specific temperature. Once you hit that point, we say the solution is saturated. It can't hold anymore. But here is the cool part. A saturated solution isn't just sitting there doing nothing. It's actually a beehive of activity. Down at the molecular level, two things are happening at the exact same time. You've got dissolution, where particles are breaking off and dissolving, and at the same time, you've got crystallization, where dissolved particles are bumping back into the solid and sticking. When a solution is saturated, those two processes are happening at the exact same speed. It's this perfect, constant, dynamic balance. Okay, so far, we've mostly talked about solids dissolving in liquids. But what happens when you try to dissolve a gas in a liquid? Well, that's when a whole new set of rules kicks in, and the number one most important factor is pressure. This whole idea is governed by a fundamental rule called Henry's Law. Now, to put it simply, all it means is that the more pressure you put on a gas that's sitting on top of a liquid, the more of that gas will dissolve into the liquid. It's a straight-up relationship. You crank up the pressure, the solubility goes up too. Okay, now for the big payoff. Let's connect everything we've just talked about: solutes, solvents, concentration, and especially Henry's Law, all the way back to our original riddle about soda, scuba diving, and surviving on a mountain. You know that fizz in your soda? That is literally Henry's Law in a can. To make soda, the factory forces carbon dioxide gas into the liquid under super high pressure. As long as that can is sealed, the pressure stays high, and the CO2 stays dissolved. But the second you pop the top, whoosh, you release all that pressure. The gas isn't soluble anymore, and it rushes out of the solution as thousands of tiny bubbles. Now let's take that same exact principle to a much more dangerous place: deep-sea diving. The deeper a diver goes, the more intense the water pressure gets. And just like the CO2 in that soda can, the nitrogen gas from the air in their tank starts to dissolve in greater and greater amounts into their bloodstream because of that intense pressure. And this is where it gets terrifying. If that diver comes back to the surface too fast, the pressure drops rapidly. It's just like opening the soda can. All that extra nitrogen that was dissolved in their blood suddenly comes rushing out of solution, forming painful and sometimes deadly gas bubbles in their joints and tissues. This horrible condition is called the bends, and it is a direct, life-threatening consequence of Henry's Law. So, to fight this, professional divers don't just breathe regular air. They use a special mix, often one that contains helium, because helium is way less soluble in blood than nitrogen is. This specially designed solution helps stop a dangerous amount of gas from dissolving into their blood in the first place. And finally, let's go from the bottom of the ocean to the top of Mount Everest. Up there, the problem is the exact opposite. At high altitudes, the air pressure is really, really low. That means the pressure of oxygen is low too. So according to Henry's Law, that low pressure means less oxygen can dissolve from the air in a climber's lungs into their blood. This starves the body of the oxygen it needs, leading to weakness, confusion, and a really dangerous condition called anoxia. So there you have it, from the fizz in your drink, to the dangers of the deep sea, to the thin air on a mountaintop. The rules of solutions are everywhere, quietly shaping our world in ways we almost never see. So the only question left is, now that you know the rules, what invisible solution are you going to notice next?